So homology group is a concept that is used along with chain complex also. So in chain complex, we know that we start with Cn um, vector space, which is over complex K. Then we go to Cn minus 1, then Cn minus 2, all the way till 0, right? For each this chain group, for each chain group, we also define another group, and that is called homology group. So corresponding to this particular chain group, if we have homology group Hn, right? And for corresponding to this chain group, we have homology group Hn minus 1. For this, we have homology group Hn minus 2. So for each chain group, we have a homology group. But how to find that homology group, and how do we define that homology group? For that, we have to learn two more things. One is uh, Zn. So here n means it is associated with Cn. If I write n minus 1 in subscript, then it is associated with Cn minus 1, right? So this subscript, always remember that subscript refers to the dimension of simplices that we are dealing with, or dimension of the simplices of a particular vector space. So Zn is our kernel of Dn. What is Dn? Dn is a boundary operator for Cn, right? So Dn will map Cn to Cn minus 1. And what do you mean by kernel? Basically, kernel is those set of inputs. So in any function, we have input x that goes to y, right? So for here, for uh, this dn or dn function, we have input as cnk and output as cn minus 1k. One thing is that kernel of dn, kernel of function dn, so function kernel of function dn uh, is set of inputs that belongs to this Cn, right? So we have some, now in Cn we have some vector, we would have some basis. By using those bases, we can generate many vectors or many chains. We have to pick those chains from the input which map to 0 in the output. So those input in X, so if I put any let's say we have an input x1. So if I put x1 in my function, if that is yielding me 0, if x1 is yielding me 0, then x1 is a member of kernel of function f. Okay, so if here we don't have any function directly, we have maps of one vector space to another vector space. So we have this x vector space and we have this y vector space. So for this function, here function, we have this boundary operator. So in input, we have to find out those inputs which will map to 0, right? So for example, here we were having this v0, v1, v1, v2, right? For c1, what will be the kernel? What will be the kernel? Kernel will be, I have to pick those values of n1 and n2. For that, it will become equal to 0. So if I choose n1 as 0, n2 as 0, n3 as 0, so what will I get? I will get a 0. So that will map to 0, right? But that will be very trivial vector. If there is any general non-zero chain or vector which is becoming equal, which is evaluating to 0, right? That that vector on which if I apply the boundary operator, so if if I apply boundary operator over here, and if that is becoming 0, let's say if I choose some value of n1 and n2 and n2 and n3, on which if I apply the boundary operator, so it we apply del 1 boundary operator, if that is becoming 0, then that group is a part of kernel, right? And I hope the kernel is clear. Now one next thing we have is uh, this bn. So bn is image of dn plus 1. So we have to uh, be very careful here, because for Jden we are finding a kernel of same boundary operator, but for bn we are founding the image of dn plus 1. So we are moving one step backward. So here we have cn plus 1. For cn plus 1, what is the image, right? So what are the images that I am getting uh, if I apply boundary operator on? For if I found homologous group for, if I finding bn for this cn minus 1, then for it image bn will be this one. So if I apply dn over here, and I get the image here, right? So image is on the range side. So image we find here, right? So image is the output side, in the side of range. This one is bn. So Jden is also some vector space. Okay, so this Jden is also a vector space. uh, Vector space. So it is a generalized vector space which have all those which will generate only those vectors which will map to 0 in the output. And in bn we have all the output, all the vectors uh, which are coming by applying this del n plus 1, right? So which are coming from the chain complex which is backward. So for cn minus 1, image will be all the outputs we are getting by applying del operator on cn. So vectors we are getting from here to here will become the part of image of for cn minus 1. And to compute the homologous group hn, for that we have to just take the kernel of dn and subtract the set or the set of vector space of image. That will give me the homologous group. So again, hn is also a vector space, just like chain group. Hn is a vector space, and it is also called quotient vector space for cn chain group. So we have to think about we have to in the given question we have to find out all the inputs in particular cn which are mapping to 0. Get that set of Zn. You can get the Zn set, you can generalize it, you can write it. And for bn you can get the set of all those images which I'm getting from previous chain group by applying the boundary operator corresponding to it. So when I subtract all those images from my kernel, I get my homology group, and this is also called quotient vector space.